Hi guys. Good morning. This is Dr. Math speaking. We're going to talk about exponentials today. And this is the US cases we have so far of the coronavirus. And as you can see, this is not a regular line. This is going up like crazy, right? It's really jumping up really fast. This is yesterday, sorry, the day before. So as every day passes, we have more and more cases in the US. We're going to try to find out what's happening. And for that, we're going to use exponentials. Okay? So let's see what's going on every day, what's happening. So yesterday was March 17, and we had 6,411 cases. The day before, we had 4,663. And like this, we would like to know every day what's the rate of change, how much this is changing every day. To know that, what we're going to do is we're going to divide 6,411, which is yesterday, over the day before, 4,663. And if we do this math, what we find is that actually every day that passes, we have something, a multiplier that it's close to 1.3. It's 1.37 for from March 16 to March 17. Okay. Then if we do the same thing for March 15 to 16, we actually get 1.27. For this jump here, we get 1.25. For the day before, 1.31. Okay, and 1.37 for this jump here. So as we can see, it's close to 1.3. That's the jump we have every day. So that means that we can use this math to predict what's going to happen tomorrow, right? So for March 18, if we multiply, I'm going to use the calculator for that, right? If we multiply 6,411 times 1.3, what we're going to have for today, more or less, is 8,334 cases, okay? Unlike this, but what happens if we would like to actually know how many cases we will have in a week, or in a month, or in 2 months? Multiplying times 1.3 to get to that point would be a lot of work. So it's convenient, it's practical to try to find a function that we can use so we can put any day there and it works, right? So to do that, we're going to use exponentials, okay? Oh, by the way, before we get to that point, I wanted to show you that actually, if we look at January, China, and we do the same math, okay, in between 27th of January and 20th of January in China, if we do the same math here, we're also going to find, even though that it's like more than a month and a half ago, we're going to have the same multiplier, which is 1.3. This has to do with how infectious is this disease, right? It has to do with biology. So if we try to understand how to model this data that we have here, how do we can find a function that models this data, we can use exponentials, okay? So exponentials work this way. Exponentials are equations that actually they have the variable as exponent in here. That's why we call them exponentials, because the variable, it comes here as an exponent, okay? Now, in our case, this variable represents number of days, right? So we're going to put like 1 day or 2 days or 3 days, and this function is going to compute what's the total number of cases, okay? This would be the initial value. A stands for the initial value. Okay. B has to do with the rate of change, how rapidly this is changing. Okay. And again, for our cases, this would be the number of days. Okay. If we look more closely how B is built up, we have the B actually has two different things in it. This one that represents that actually the cases don't disappear. So for tomorrow, we're going to have the cases of today plus whatever it's new. So this one represents whatever we already had, and this one represents whatever it's new, the rate of change. So we can have three different scenarios. If the rate of change is positive, then we have a growth, as we have right now. Every day, the number of cases is getting greater, right? So it goes up as a function you have seen before. While when R is below 0, which means that it's negative, what we have is a decay, which means that at the beginning we had a really big number, but it's going down, 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 down. That's decay. And we have several scenarios in life which actually we have a decay. Okay, the most famous one has to do with radiation. Okay, with nuclear decomposition. Okay, and then the last one is when R equals 0, there's no change at all. That means that we only have the one, and that's when we multiply something times 1, we're actually doing nothing. Right? So it doesn't matter how big this is gonna get. 1 to the 10 is 10 times 1, right? I mean, 1 times 1 times 1 is 10 times, which is 1. So it's not going to change. So this is not going to change. So if it doesn't change, then we have just a line, okay, a horizontal line. So knowing this, knowing how this works, we're gonna apply all this to what we have right now, to this coronavirus situation. Okay, so let's try it. So as this is just changing, as we said before, it's just increasing every time by times 1.3. What we're gonna write for our base is, okay, so I'm gonna try to write it here. Instead of P, I'm gonna use CC for coronavirus cases. Instead of X, I'm gonna use T for days. And then A is the initial value, okay, as during March 17, which was yesterday, okay. We're gonna use this as our initial value. So it's 6,000, that's the A, 6,411, okay. And then times 1.3, which is our base, right, to the power of D. Great. So that means that if the input is 0, and 0 stands for, I'm gonna write it here, 0 stands for March 17, which was yesterday. Today is going to be 1, which is March 18. 2 is going to be March 19. This is the day. Okay. So if we input a 0, we're going to have is 1.3 to the 0 power, right? Anything to the power of 0 is, here we have make, and make is a student. Look, here's make. Hi, make. So this is a popular guy in Barcelona, okay, in Barcelona TV, and Mick is gonna help us. He's one of my students. So Mick, how much is 1.3 to the power of 0? Is it 0? No, Mick, it's not 0, because as we know, anything to the power of 0 is always 1. Oh, yeah, you always forget. Okay, Mick, try to pay attention, okay? Yeah. Okay, so let's go for it. So anything to the power of 0 is 1. So all this is going to be 1. This is not going to change. So we're going to have still the same value, okay? So again, this is for March 17, right? Now, if the input is a 1, then we have so now we have 1.3 to the first power, which is actually 1.3. So, because it doesn't change, right? Anything to the first power doesn't change. So we have 6,411 times 1.3, which get us 8,334, right? Now, what happens if I would like to know what's gonna be the coronavirus cases in a week from today? Today it's 1, so in a week we're gonna have to add 7 to this one, right? So we're gonna have number 8. Okay, that will be next Wednesday. So now it's 6,411 times 1.3 to the 8th. So now we take the calculator. We actually do this. So we have 6,411 times 1.3 to the power of 8. What do we get? We get 50. Look at this. Look how crazy it grows. Now we have 52,296 cases in the US in a week. Right? So it grows really crazy. So what about if I would like to know how long it's gonna take to reach 1 million people infected in the US? Imagine that. So that we're talking about coronavirus cases, right? So now instead of let's build the equation first, right? Well, it's actually here. I don't have to write it again, right? It's here. Now in here, what I did is, okay, the input 1 stays, so I said, okay, day 8, how many cases are we gonna have? But now this is a different situation. I'm asking how many days is gonna take to reach 1 million, and the 1 million cases, right? So I would have, now how I will write this equation is, okay, 1 million cases equal, right, this equation, correct? So so now how do I solve this equation? It's something that we don't know how to solve, right? To solve this equation, we need to be good at solving exponentials. And I'm gonna do this in the next video, okay? But now, before we finish this video, let me show you something you can do with this calculator. And remember, if you don't have this calculator at home, you can always install in your cell phone just an emulator. So if you look in your app store for TI-84 Plus or TI-84, you're gonna find apps that look like exactly like this calculator. Okay, so now I'm gonna try to actually plot this function here to see the table, and this is gonna be very good for the ACT. So it's good that you know how this works. So let's let's type this function in here, okay? So we have 6,411 and then times 1.3 to the power of x, okay? Good. And now this calculator can graph this function. Just thinking here, that takes a long time, trying to graph. Okay, nothing comes up. If nothing comes up, that means that the window might not be right. So if we want to see something, as this is very big, we should actually change the window. So we're gonna put from well, the y max that we want to see, it's let's say like 100,000 maybe, and then yes, let's see if now it works. Let's graph it again. Look, it's starting to graph here. You see, if we change the window, now we're seeing what's going on, right? Good. So we get this exponential. And now let's go to table set. No, not table set, sorry, table. So I'm doing second and graph. It says table in here. And I can actually use this to get how many days it's going to take to be 1 million people infected. That would happen if our authorities do nothing, right? But that's the reason why we're not in school right now. So if we look at this data, it's going to take like here we go. This is almost 1 million, so it's going to take 20 days to be 1 million people infected. Okay, so you understand how it works. Okay, I hope this video helped. The last thing I would like to tell you guys is that how to compute the rate of change. And if we look here, yeah, how much is R in this coronavirus situation? How much is R? So if the whole thing is 1.3, and here we have a 1, how much R must be so the whole thing is 1.3? So Mick, what do you think? Is it 0.3? Yes, Mick, great. So it's 0.3. So that means that in our example, R is 0.3. It's positive. We have a growth, right? Now, if we want to express this 0.3 as a percentage, that would be, we multiply times 100, okay? And we can get it as a percentage. So how much is 0.3 times 100? Well, when we multiply times 100, what we're doing is just we're moving this point 2 times, right? So if we move it 1 time with 3%, but if we move it 2 times, it will be 30%. Okay, so the growth it's 30%. That's really high, because that means that more or less, look at this. If we look at this, it takes 1, 2, 3, 4 days to double. All right, because here we have 2,200 more or less. Here we have no. I'm sorry. It takes It takes 1 to 3 days to double. You see that? Because 30% plus 30% plus 30%, right? That's 90%. So that means that in 3 days, 1, 2, 3, more or less, this is double. So that's crazy, right? The way it grows is really fast. So that's the video for today. And then tomorrow we're gonna work really hard on how to solve exponential equations, so we can do this. We can solve this equation here without the need of what we did with the calculator. Have a great day. Bye-bye.